Hello.
Hello, sir. Good morning.
Hello, sir. Good morning.
Yeah, good morning. They have started complex numbers.
Yes,
Yes.
sir.
Okay. Okay, so we'll also begin that only. After that, we'll do circles. So the idea here is that this is a new type of number which is two-dimensional. So in the sense that normally all real numbers you could have represented on a single line called the real line. And you could have said that, okay, 0 is here and positive numbers this side, negative numbers this side. Any number can be represented, any real number can be represented on the number line. So now, so basically you need just one quantity to decide what is a real number. Here you need two quantities. So we are going from a single unidimensional numbers to two-dimensional numbers. So two-dimensional numbers in the sense that any point in the plane will now be represented by a number. So earlier you had points on a line, which is a single dimension, which is real numbers. Now you will have any point in a plane, which can be represented by a number. That number is a complex number. So obviously, just like in coordinate geometry, you can represent any point in the plane by an ordered pair x comma y. So x is going to be this distance and y is going to be this distance, right? So here also what we will say is this is the real axis and this is the imaginary axis, and we will call any point x comma y on the plane as we'll say that this point represents the number x plus iy, where I is a symbol. I is just a symbol which stands for root of -1, or basically I square is supposed to be -1. So if you construct numbers like this, then you are basically going to be able to write any point like in the plane using this method. So if this point is 2 comma 3, it will be 2 plus 3i. If this point is -3 comma 1, it will be -3 plus i, 1i. This point could be -4 minus 2i. And this point could be 4 plus 4 is positive and I minus 2. Y is negative, so minus 2i, let's say. So basically x denotes the real part and y denotes the imaginary part, and I is a symbol which connects them. So the reason we are coming up with this type of numbers is because generally, like, we thought of numbers when we started trying to solve equations. So for example, x plus 1 is equal to 0 didn't have any solutions, no solution in natural numbers. Like if you just knew about natural numbers, this doesn't have any solution, there is no natural number. So then we said x is equal to -1 and we defined something called the integers, right?
Yes.
So we went from the set of natural numbers to the set of integers because we couldn't solve this equation. Similarly, if you wanted to solve this equation, you have to not be just in the set of integers. You have to go to the set of rational numbers. X belongs to Q, rational numbers. No integer will solve this. So this equation, to solve that, we had to extend it to rational numbers. Similarly, we had to extend to solve this equation, we had to construct irrational numbers. And in the same way, like basically all of these numbers are things that we constructed or mathematicians constructed in order to be able to solve some equations. And all of these are equally like imaginary, like in the sense that any number is a abstract concept, it's not something real. Any number is an abstract idea. So even though we use the term real numbers, it's not like the numbers are real, like they are concepts in our mind. So similarly, we had to extend we wanted to solve this equation. So this equation cannot be solved in the set of real numbers also. So we are extending the set to include numbers like this. So you will say x is equal to root of -1. This is the number I.
So your voice keeps breaking in between, and there's also some lag.
Okay. I don't know what to do about that, but yeah. We have basically this set of numbers constructed just to solve equation like this, of this form. No real solutions are possible. So algebraically, this is the reason why complex numbers were developed, to be able to solve equations which had no solutions in real numbers. However, people discovered a geometric interpretation of that. People saw that, okay, if you put it on the x-axis like this and y-axis like this, and any number you can split into two components now. You will have one real part of it and one imaginary part of it. This is y, this is x, and the number will be called x plus iy. Then this number is a complex number. So in general, a complex number will be represented by, complex number can be written as a plus ib, where a is the real part and b is the imaginary part. The terms real and imaginary are misnomers, because actually all numbers are imaginary. Like 1 and 2 and 3, these are also imaginary, because these are some things that we have made. It's not something real. So a complex number, you should not think of complex numbers as something imaginary and real numbers are actually real or something. Everything is imaginary. We have only constructed everything. So it's on an equal footing with the set of real numbers. Like it is just another new type of number that we have constructed, just like we constructed so many different types of numbers, rational numbers, irrational numbers. All of those are also our own conceptions. So similarly, this is a new type of number. And if we say z is a complex number a plus ib, we will say real part of z is a and imaginary part of z is b. And once we have this construct, we will like to do operations on these numbers similar to what operations we do on real numbers. So what we want to do is add, subtract, multiply, divide. Addition, subtraction, multiplication, division. These are basic operations that we like to do. So how do we add and subtract complex numbers? So if you have two complex numbers, a plus bi and c plus di, the way you add is you get a third complex number z is equal to a plus c plus b plus di. So you basically add the real parts together and the imaginary parts together, and this is a new complex number. This is the real part and this is the imaginary part. And geometrically you can see that this makes sense, because if I had a number here z1, which is say 1 plus 2i, so this is 1 and this is 2, and I had a different number z2 which is 2 plus 1i, so that means that this is 2 and this is 1. Then if I add these two, I will get, according to our rule of addition, I will get 3 plus 3i, which means 1 plus 2 on the x-axis, so somewhere here and again somewhere here. This is your 3 plus 3i. So basically what you're doing is adding this and adding the real part and the imaginary part. So you can think of this as a vector addition also. So z plus 2i would be this, 1 plus 2i will be this vector, and 2 plus 1i would be this vector, and the addition will be this vector, which is the resultant of these two vectors. So there is a geometrical sense in which the addition makes sense, because you can see that you're just like you would have if you had two vectors, I cap and j cap components would have been added together, and you would get a resultant vector. In a similar manner, you're doing the same thing here. Complex numbers are there, and you are adding the real part and the imaginary part separately. So that is addition. Subtraction is similar. Z1 minus Z2 would be if Z1 was A plus BI and this was C plus DI, then your subtraction would be simply A minus C plus B minus DI. So that is your subtraction. Now for multiplication and division, let's say we want to do Z1 into Z2. So if this is A plus BI and this is C plus DI, so the multiplication is defined like this: AC minus BD plus I times AD plus BC. Now you would have an obvious question of why are we defining multiplication in this weird way? The reason we are defining a weird way in the sense that you could have tried to define multiplication in a different way also. You could have said multiplication is AC plus BDI, which seems more natural, right? Like if you have A plus BI, C plus DI, I could have said multiply the real part and multiply the imaginary part and say this is the multiplication, right? But
Yes.
this is not a proper definition, because I mean the choice of defining an operation is totally up to us. But what we want to do is define operations which make many other things that we are familiar with still work. So we are familiar with a distributive law of multiplication. Distributive law of multiplication is something like this: A into B plus C in real numbers is AB plus AC. We are also familiar with our geometrical understanding of complex number, which is a point in the two-dimensional space. So what we want to do is preserve all of these things when we define the operation of multiplication. So this definition doesn't preserve any of that. So this is not the definition. The way you define multiplication is simply do the same things that you would do in algebra. So if you had two expressions in algebra and you have to multiply these two, what would you do? You would just do normal term by term multiplication, right? So if you do term by term, it will be AC plus ADI plus BCI plus BDI square, right?
Yes, sir.
And this I square becomes -1, and you say AC minus BD plus I times AD plus BC. So actually, the multiplication is defined in such a way that your normal algebraic manipulation still makes sense. So this this is the multiplication. This is what we get when we multiply two complex numbers. So that is how it has been defined, so that you can do normal algebra. Like the way you have learned it before, that continues to be valid. So that is your multiplication operation. Later, we will see geometric meanings to that. Geometric meaning to that will be clear later in a future class we'll discuss. For now, we'll just know how to do the multiplication if there are complex numbers given. If you want to do division, for example, Z1 by Z2 you want to do. So you want to have A plus BI by C plus DI. Now here, ultimately you want to get a new Z3, and Z3 will also have some real part and imaginary part, which is the division of Z1 and Z2. So in order to get that Z3, which has a real and an imaginary part, what we do is this: A plus BI by C plus DI, you multiply by the conjugate. Conjugate as in C minus DI, C minus DI, up and down. Because this multiplication helps you make the denominator a real number. So if you do this multiplication, you will realize that it is becoming AC plus BD plus BC minus AD I on top, and divided by this becomes C square minus D square I square, and I square is -1, so this becomes AC plus BD plus BC minus AD I divided by C square plus D square. So now this has become a real number. So we can just separate out the thing into two separate fractions. And you can say AC plus BD by C square plus D square plus BC minus AD by C square plus D square. This becomes your new complex number because this is real and this is real. A complex number always has to be represented as a combination of one real part plus I times another real number, which is the imaginary part. So we wanted to get it into this form, and that is what we have done by multiplying by conjugate. So Z1 by Z2 is equal to this complex number, and this is your Z3. Obviously, you don't have to remember this. You have to do it when the time comes. If you have to multiply, just do this operation. Don't try to remember all this. All of this is straightforward algebraic manipulations, by the way. You have to just keep using the symbol I square is equal to -1 whenever it comes, right?
Yes.
So there is no issue. You just keep multiplying, and whenever I square comes, you put it as -1, right? So
Yes.
this is
Yes.
your multiplication. Now, after this, what we will see is some properties of addition and multiplication. So properties like, we'll see commutative law. So commutative law means that if I add Z1 plus Z2, it is the same thing as adding Z2 plus Z1. So this is commutative. And Z1, Z2 belongs to the set of complex numbers. The set of complex numbers is written by the symbol capital C. And you will realize that the set of complex numbers is the superset and real numbers are inside. Basically, you can say that all real numbers are complex numbers because real numbers will be something like this, right? √2 is a real number or 3 is a real number. You can always write √2 as √2 plus 0 into I and 3 as 3 plus 0 into I. So basically what we are saying is if you have numbers, all the numbers on the plane are complex numbers, any number on this two-dimensional plane. So obviously the real number line is part of that, right?
Yes, sir.
So the set of complex numbers is the superset for set of real numbers. And it follows the commutative law of addition. It also follows associative law. Associative law is Z1 plus Z2. If you group this and add like this, it's the same thing as grouping the last two and adding. There is no issue here. Then there is an additive identity. Additive identity means there is a number, there is a complex number 0 belongs to complex such that Z plus 0 is equal to Z. So there is a complex number 0 which is such that any other complex number if you add you will still get the same complex number. So this is the additive identity. There is also an additive inverse. Additive inverse in the sense that there is a complex number minus Z such that if you add Z plus minus Z, you will get the additive identity. You will get 0. So if I have A plus BI, I can construct an other complex number minus A minus BI, and that will add and cancel it and become 0, right? Then
Yes.
similarly, you have other properties. This property is for multiplication. Commutativity is true for multiplication also. Z1, Z2 is equal to Z2, Z1. Then there is multiplicative identity. Z1 into 1 is equal to Z1. 1 is a complex number. 1 is the multiplicative identity. Multiplicative identity. So in the sense that you multiply any complex number, you get the same thing. Associativity is true for multiplication also. If you do this into this, it's the same thing as this into this. Group these two and multiply, that's the same thing. There is also for any complex number, for any complex number z, there is also a multiplicative inverse. There is a number, unique number, you can call it z power minus 1, such that z into z power minus 1 is equal to 1. So therefore z power minus 1 is equal to 1 by z basically. And how do you find this multiplicative inverse? You have to just find the value of 1 by z. So 1 by z will be 1 by a plus bi, and you can multiply by a minus bi by a minus bi to get a minus bi by a square minus I square b square. So a square plus b square. So z inverse is coming out to be a by a square plus b square plus minus b by a square plus b square into I. So this is the multiplicative inverse for any complex number a plus bi. Now, with these properties, we can now start defining the laws concerning exponents and all. So exponents in the sense, you can now take complex numbers and do repeated multiplication, right? You will have these results. Z power m, z power n will be equal to z power m plus n. The normal laws of indices and all will still be valid, because z power m is just z into z m times, and similarly z power n is also the same thing. So similarly you'll get z power m by z power n is equal to z power m minus n, and you will get your normal laws z power m power n is equal to z power mn, and z1 into z2 whole power n can be written as z1 power n into z2 power n. And similarly you can write z1 by z2 whole power n will be z1 power n by z2 power n. So all of these normal laws that you expect are still valid, and basically you have your algebraic representation of complex numbers in this way. You should also know what happens if you take I and get powers of that. I is defined as root minus 1. So I square is minus 1. I cube is minus 1 into I. So minus I. And I power 4 will be I square power square. So 1. So after that, it will start repeating. I power 5 will be I power 6 will be again minus 1. I power 7 will be minus I, and I power 8 will be again 1. So the pattern keeps repeating after 4. You get this is I only, and I minus 1 minus I 1, and same thing is happening again. Higher powers, right?
Yes.
Yes, sir.
Then we will talk about a complex numbers conjugate. So conjugate of a complex number. So if you have a complex number, let's say z somewhere here, which is a plus bi, z is a complex number like this, then we can define a new complex number which is z conjugate, which is defined as the reflection of z over the real axis. So this is 90, this is equal, this is equal. If you reflect the complex number over the real axis, then you get a new complex number, which is called the z conjugate. So obviously, if you just do this reflection, you will realize that the real part remains the same, right? It's just that the imaginary part has become, instead of b, it becomes minus b, right?
Yes, sir.
So z conjugate for any complex number z, conjugate is a minus bi. Z conjugate is a minus bi. So that immediately means that first property is z is equal to z conjugate if and only if what will be 0? B should be 0, right?
Yes, sir.
A plus bi will be equal to a minus bi only if b is 0, right? And
Yes, sir.
if b is 0, if b is 0, then the number is a real number, right? That
Yes, sir.
z is a real number. So z is equal to z conjugate means that z is a real number. It is on the number line here. Then only the reflection is the same. So the second thing here is, if you multiply z and z conjugate, you always get a real number, because you'll see a plus bi into a minus bi will be a square minus b square r square. So it is a square plus b square, right? So this is a real number, and it is a positive real number. So z multiplied by z conjugate is always a real number. Then we can say that if we have z1 plus z2 and we take the whole conjugate, it will be equal to z1 conjugate plus z2 conjugate. So let's take z and z1 as a plus bi, z2 as c plus di. So z1 plus z2 will be a plus c plus b plus di. And if you take whole things conjugate, you should get a plus c minus b plus di. And if you split this apart, it will be a minus bi plus c minus di, which is individual numbers conjugates, the addition, right?
Yes, sir.
Yes.
So the property is that z1 plus z2 whole conjugate is equal to z1 conjugate plus z2 conjugate. Similarly, like you can easily prove that z1 into z2 whole conjugate is equal to z1 conjugate multiplied by z2 conjugate. Just put a plus bi c plus di, you will get it. Just check whether this is true or not. And you can also say that z inverse whole conjugate is equal to z conjugate inverse. So again, this will take a little more effort to prove, but you can start off with z is equal to a plus bi, find out z inverse. We already found out that. So it will come as something a by root over a square, not root over, a by a square plus b square minus b by a square plus b square, something like this it will come. And if you take the conjugate of this, z inverse conjugate, it will be a by a square plus b square plus bi by a square plus b square. And now you can say z conjugate would be a minus bi, and take the inverse of that. So 1 by a minus bi. So you will write it as a plus bi by a square plus b square, right? So it will come out as this again. So what we can see here is that this property will hold. And similarly, this property will also hold. You can say z1 by z2 whole conjugate will be equal to z1 conjugate by z2 conjugate. So these are properties of conjugate numbers. This multiplication property can be extended. Like you can have multiplication of many complex numbers, and conjugate of that will be multiplication of the individual conjugates. All of this is true. Yeah. So these are standard properties of conjugate of a complex number. Is everyone understanding what is happening?
Yes.
Okay.
Yeah.
Then the next thing that we look at is modulus of a complex number. Modulus of a complex number. So if you have a complex number z here somewhere, which is a plus bi, then modulus of z denotes distance of z from the origin. So this distance is mod of z, written as mod of z. So mod of z is obviously going to be root over a square plus b square if z was a plus bi, because of Pythagoras theorem. This is b, this is a, so the
Yes.
hypotenuse will be root over a square plus b square. And mod of z is going to be real, going to be a real number, because it is a distance and distance is real. So anytime you have mod z, you mean basically root over the real part plus the imaginary part squares. So there are very obvious properties of modulus that we need to understand. The first one is minus of mod z is less than equal to real part of z is less than equal to mod z. This is obvious because real part of z is what? Real part of z is simply a. So we know that minus root over a square plus b square is less than equal to a is less than equal to root over a square plus b square, right? Because these quantities are larger in size, right? So this is true. Similarly, you can also say that minus of mod z is less than equal to imaginary part of z is less than equal to imaginary part of z, right? Less than equal to mod z. Again, this is true because this is b and this is minus root over a square plus b square, and this inequality is true. Correct?
Yes, sir.
This property is useful sometimes, so you should write it down or make a note of it. Then the second one is
Back to the previous page, which is for the second page. Yes, sir. Thank you.
the second thing is mod z is greater than equal to 0 for all z belongs to complex numbers. So basically, since it is root over a square plus b square, the lowest it can be is 0 when you have the 0 complex number, when a and b are both 0. But otherwise, it will be greater than equal to 0. So that is an obvious thing. Then we have mod of z is equal to mod of minus z is also equal to mod of z conjugate, because this is mod of a plus bi, which is equal to mod of minus a minus pi, which is equal to mod of a minus pi. Because all the time, like think of it geometrically, the distances of all these three complex numbers is going to be the same. If you draw a figure and you have one complex number here, minus z is going to be negative, just reflection across the origin. So this is minus a minus b point. And this is going to be just conjugate, which is a minus bi, right? This distance will be equal to this distance because I'm doing a reflection here and this triangle is congruent to this triangle. And similarly, this distance is also equal. So all these three distances are equal, right?
Yes, sir.
This will be your mod of minus z. This will be your mod of z. And this will be your mod of conjugate. So you can take mod for any complex number basically. And similarly, now we can see that z into z conjugate we saw earlier was equal to a square plus b square in the previous section. So that is obviously just mod z whole square. So you get z into z conjugate is equal to mod z whole square. This is a very important identity used many times. So it should be obvious why. Like you're doing a plus bi into a minus bi. The multiplication is a square plus b square, which is just mod z whole square. Right?
Yes, sir.
Okay. Then the next thing is mod of a product. If you take a product of two complex numbers, mod is equal to mod z1 multiplied by mod z2. You can confirm this yourself. It's easy to prove. Just take two different numbers, multiply, take mod. Then now we come to the important stuff. Okay, before that, mod of z inverse is equal to mod of z to the power minus 1. Why? Because z was a plus bi. We saw earlier that z inverse was a by root a square plus b square minus bi by a square plus b square. So if I take mod of this z inverse, I have to do root of this square. So a square by a square plus b square whole square plus minus b whole square by a square plus b square whole square. So this will become a square plus b square by a square plus b square whole square. So that is simply going to be 1 by root over a square plus b square. And that is equal to 1 by mod z, right?
Yes, sir.
So this identity is true. Here you have an inverse of a complex number and you're taking the mod of that. It is equal to the complex numbers mod 1 by that, 1 by the complex numbers mod. So That is true. And similarly, mod of Z1 by Z2 can be proven to be equal to mod of Z1 by mod of Z2. Now, these are stuff that you can easily derive. Now, the next one is very important. This is the triangle inequality. So this comes in handy in many problems. So you should be aware of this property. This is saying that mod of Z1 minus mod of Z2 is less than equal to mod of Z1 plus Z2 is less than equal to mod of Z1 plus mod of Z2. And similarly, you can write another version of the same thing. Mod of Z1 minus mod of Z2 is less than equal to mod of Z1 minus Z2 is less than equal to mod of Z1 plus mod of Z2. These two inequalities together are called the triangle inequalities. And if you think about it, it should be obvious why this is true, because I mean, you can prove it by taking a plus bi and stuff also, but think about it geometrically. If you have z1 and z2 somewhere here and somewhere here, this is z1, this is z2. Mod z1 is this distance, and mod z2 is this distance. So if you do mod z1 minus mod z2, it can come as something negative also, right? Because it is possible that this distance is less than this distance.
Yes, sir.
However, if you do z1 plus z2, and that will be your complex number somewhere here, which will be having a longer mod. So, and anyway, mod of any complex number cannot be negative. So this part of the inequality is true, right?
Yes,
This
sir.
can be negative. This is not never negative. And even if this was not negative, it will be lesser than the distance when it is this complex numbers, mod z1, z2, right?
Yes, sir.
Yes, sir.
And this thing will be lesser than just adding the distances, because just like in vectors, you can say that two vectors are there, the resultant vector is always going to be lesser than the lengths of these two vectors added. You can say that mod of a plus b, if you think of vectors, is less than equal to mod of a plus mod of b, because this thing is actually root over mod a square plus mod b square plus 2ab cos theta, right? And this thing is going to be equal to this only when cos theta is 0, cos theta is 1. So when the angle between the vectors is 0, then only when you add, they get added, their lengths get added. If the angle between the vectors is non-zero, your addition of the lengths, which is this thing, no, addition of the lengths, which is this thing, is always going to be greater than the resultant's length, right?
Yes, sir.
Basically, what we are trying to say here is mod of this is what? This is a plus c plus b plus di. So a plus c whole square plus b plus d whole square is less than equal to, this is root over a square plus b square plus root over c square plus d square. This is what the inequality boils down to, and you can prove it algebraically. You can try to take squares and all, and try to prove this true as an algebraic statement, but it is an obvious geometrical fact. Like, only if the two vectors or the two complex numbers were on the same line. So if you had something like this, 1 plus 1i and 2 plus 2i. So let's say this is 1 plus 1i, 1 comma 1, and another complex number was 2 comma 2. So then when you say mod z1 plus mod z1 is root 2, mod z2 is root 4 plus root 4, so 2 root 2, and z1 plus z2 would be 3 plus 3i, so that will be somewhere on the line but ahead, 3 plus 3i. So mod of z1 plus z2 would be 3 root 2, which is the addition of root 2 plus 2 root 2, right? Only then, if the complex numbers all lie on one line, then you can say that the equality holds. Otherwise, it will be lesser than that, right?
Yes, sir.
Correct. So these two you should write down. These are very important. So difference of the mods is less than equal to the mod of the summation or difference, and that is less than equal to the sum of the two mods. So this is the triangle inequality for complex numbers. Then now we can try and do a couple of questions. Yeah, now we can try some problems. We have seen properties of complex numbers, mods, conjugates, and basic operations on complex numbers. Now we can think about some questions. There is obviously a lot of theory left, but we'll do that in the next class. So for example, prove the identity mod of z1 plus z2 whole square plus mod of z1 minus z2 whole square is equal to 2 times this plus this. This is the first one. Then prove that if mod z1 is equal to mod z2 is equal to 1 and z1 z2 is not equal to minus 1, then z1 plus z2 by 1 plus z1 z2 is a real number. Okay, so try these two questions first. Try these two. You have 5 minutes. First one should be obvious, right?
Yes, sir.
You just take a plus bi and c plus di, and you will get after doing the operations.
Yes.
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 Second one, you have to prove that this is a real number. That means its imaginary part should be 0. Or you can say that the conjugate of this should be equal to itself. So you can try to prove that z1 plus z2 by 1 plus z1 z2 whole conjugate is equal to z1 plus z2 by 1 plus z1 z2. Because we saw a property that whenever z is equal to z conjugate, z is real. Right?
Yes, sir.
Yes, sir.
So using the properties of conjugate here on the left hand side, you can say that it's a conjugate of two complex numbers a by something by something. So that can be written as the top part's conjugate divided by the bottom part's conjugate. And again, using the properties, this is z1 conjugate plus z2 conjugate divided by 1 conjugate is 1 only because 1 is real, plus z1 z2 conjugate, right? And this becomes z1 conjugate plus z2 conjugate by 1 plus z1 conjugate z2 conjugate. I'm using all the properties of conjugates here, right? So sum of the two
Yes.
complex numbers conjugate is separate conjugate sum. Product of two complex numbers conjugate is product of the conjugates individual, right?
Yes, sir.
Yes.
Now we know this, that, and we know the identity z1 into z1 conjugate will be mod z1 square, right? So mod z1 is 1, that means this is 1, so z1 conjugate is simply 1 by z1, right?
Yes, sir.
And similarly z2 conjugate will be mod z2 square, which is 1, so z2 conjugate is 1 by z2. So if you put that here, 1 by z1 plus 1 by z2 here, so what we will see is it will become equal to the RHS now. So put 1 by z1 plus 1 by z2 by 1 plus 1 by z1, 1 by z2. That obviously becomes z1 plus z2 by 1 plus z1, z2. Right?
Yes, sir.
So you have gone from the LHS and you have simplified that and you're getting this. So that is the proof. We have used all of the properties of conjugate and also this property, that z1 into z1 conjugate is mod z1 whole square, right?
Yes, sir.
Yes, sir.
Okay, then
So, sir, over here, looking at the first question, since that holds true, can we just can we say that since we have proved this, can we say that z1 plus z2 mod the whole square would be z mod z1 square plus mod z2 square plus 2 mod z1 z2?
no, why will you say that?
So because if, let's say, if that would be true, then we would still get the same result, right? And we have proved that this result is true by taking values of a plus ib and solving it. So that's why I was just asking.
Why are you saying that this is equal to this? Like,
So because in the previous question, if you would have expanded both of them like this, in this
why
fashion.
would you expand it like this? Is any rule given that you can expand it like this?
No, so there is no rule given, so we can't.
So don't assume anything. This is equal
Okay.
to, if there is no rule given, then how would you, like, what are you assuming?
No, sir, because see, if we would have done it like this, we would have gotten the same thing, right? So that's why I'm saying.
So you'll make up an, what is that logic, dude? If we have gotten this in some way, then that must be true. Like, what is that logic?
No, so I was just thinking if we would have expanded it this way, then we would have got that, right? So that's where that doubt came up.
this means this.
Yes, sir.
So if you multiply it like this, you will get z1 conjugate plus z2 conjugate plus z1 z2 conjugate plus z1 conjugate. This is equal to mod of z1 square plus mod of z2 square plus z1 z2 conjugate plus z2 z1 conjugate. How is that equal to this two?
Yes, sir. It's not equal. Yes.
Just because some identity is true, you cannot just make up new properties.
Yes, sir. Yes, sir. Understood.
This is not necessarily equal to this. This is purely real. This can be complex.
Yes, sir.
Prove that for any z, this is true or this is true. Either this or this will be true.
So that is 1 by root 2, right?
Hmm.
Yes.
You should prove this by contradiction. Proof by contradiction you have heard of, right?
Yes, sir.
Yes.
What is proof by contradiction?
So first
So
you
you'll
are
assume that. So you'll just assume that mod of z plus 1 is less than equal to 1 by root 2. And then you'll solve it that way. And then you'll say this is not possible because we're getting some wrong result once you've solved it.
That is not a correct statement here. You cannot assume just one of them. You have to prove that this is greater than equal to, how can this be not true? Like this is obviously possible. You have to prove a combination, no?
Yes, sir. Yes, sir.
What is your statement in contradiction?
Oh, so the statement would be this or mod of z square plus 1 is less than 1.
Again, that will not be working. That will not work. You have to, the meaning of this is, the original statement says either this is greater than this or this is greater than this. The contradiction statement for that would be both are less. Then only that is a contradiction. No, the statement, normal statement is saying one of them must be greater than one.
Yes, sir.
The opposite statement is not or, it is and. If both are less than one, then you say that that is not in this case. That is wrong, opposite of that. Right?
Yes, sir.
If you assume this and get some weird result, then that means our assumption is wrong. So one of them must be greater.
Okay,
Right?
yes, sir. Yes, sir.
The statement here is saying A is greater than 1 by root 2 and or B is greater than 1. You have to say A is less than 1 by root 2 and B is less than 1 implies something weird, wrong thing. That means one of them must have been opposite at least. Right?
Yes, sir.
So if you assume this, then you can simplify, put Z as A plus BI. Z as A plus BI. This inequality gives you 1 plus A whole square plus B square root is less than 1 by root 2. So you get 1 plus A whole square plus B square is less than 1 by 2. And here Z square will be equal to A plus BI whole square, which is equal to A square minus B square plus 2ABI. So Z square is A square minus B square plus 2ABI. Z square plus 1 will be A square minus B square plus 1. So whole square plus 4A square B square root. This is your mod of this is less than 1. So you will get 1 plus A square minus B square whole square plus 4A square B square is less than 1. That is your second inequality. Now, from here, you can try and simplify this a little bit. Correct. Yeah. Both of these inequalities are true. So what we get is, here you get 2 times 1 plus A square plus 2B square minus 1 is less than 0. So this becomes 2A square plus 2B square plus 2A into 2, 4A minus 1 is less than 0. And here you get, this is what we get here, 2A square plus 2, no, plus 2 minus 1, so plus 1. And plus 4A plus 2, yeah, this is correct now. And here we get 1 plus A square minus B square whole square plus 2 times A square minus B square plus 4A square B square minus 1 is less than 0. So 1 cancels and you get this thing, A square minus B square whole square plus 2 times A square minus B square plus 4A square B square is less than 0, right?
Yes, sir.
We have these two inequalities. So both of these things are negative, you're getting. If we add both of these things, you should have something still negative, right? You add these two things. So you'll
Yes,
get
sir.
A square minus B square whole square plus 2A square minus B square plus 4a square b square plus 2a square plus 2b square plus 4a plus 1 is less than 0. 2b square here cancels this part. You get 2a square plus 2a square is 4a square plus 4a square b square plus 4a plus 1, and there is a square minus b square whole square. So obviously now you can say this and this and this become perfect squares. So it is a square minus b square whole square plus 2a plus 1 whole square, this and this and this, plus 4a square b square is less than 0, which is impossible because it is the sum of 3 perfect squares. Right?
Yes, sir.
So what you're assuming is both of the things were the opposite thing you have assumed, and you got these results. And if you added, you should have gotten something still negative, but it is coming this side perfect squares. So that means that our assumption is wrong, and therefore what has been proved is at least one of those mods has to be greater than equal to, if not both. So that is the proof that we wanted to get. Then now there is a lot of stuff left, so we will just go in a sequence. There is solving equations in complex numbers. Then there is geometric interpretation. There is Euler's form of a complex number and roots of unity. There is a lot of theory left, so several classes it will take, but you should start solving your book. I'm sure there will be many beginner boxes. You should start doing it now. Tomorrow we'll do physics. We'll be doing center of mass only. So we'll continue with that tomorrow.
Yes, sir. So would it be possible for you to give us a sample?
Sample what?
Sir, sorry, I got mute by mistake. Sir, would it be possible for you to give us a sample paper just like last time?
Last time's paper you have not solved. No? Did you solve last time's paper fully?
Yes, sir. I solved it at home later.
You solved all the questions.
So no, so actually I had a couple of doubts there. Like a few doubts.
I'll see if I make a paper, then I'll share it with you. What is the topic? What are the topics that you have for the test?
So everything from the beginning, like everything that we've done till now, up to basically up to circular motion in physics and up to straight lines in math. So center of mass and complex numbers is not coming.
Okay, I'll see. Tomorrow's class will be center of mass.
Okay, yes, sir.
That's all now. I'll see you guys tomorrow then.
Thank you, sir.
Thank you, sir.
Bye.